Okay, so we're just looking at the algebraic vectors. So before we had geometric vectors, and with geometric vectors, they had a magnitude and they had a direction. When we're dealing with algebraic vectors, they're just defined a little bit differently. Same information is there. They still have a magnitude and direction, but instead of defining them that way, we actually just use coordinates, or maybe another way to think about it is we use the x and y components that make up the vector. Or in the case of a 3D vector, we use the x and the y and the z components. Okay. So here we have a vector u, and so the x, y, and z are 1, 2, and 5 respectively. There's a second vector in the neighborhood, v, and it has x, y, and z, -3, 2, and 4. And what I want to do is add those vectors tip to tail. So I would draw my u, and then I would draw my v. And in the old days, we'd do some complicated, horrible cosine law stuff, and it would take us forever. But with our new algebraic vectors, our fancy new algebraic vectors, we actually, all we have to do is just add x, y, and z components and get the resultant. Okay, so components are a beautiful thing. So u plus v is -2, 4, and 9. Okay, so yeah, just that, how easy is that? So yeah, the component approach wins every time. Okay, if this was u minus v, basically I'd just be subtracting coordinates, and so this would be 4, 0, and 1 if it was u minus v. So the components are really easy to deal with. Okay, this is multiplication by a scalar. Okay, so addition and subtraction are straightforward. We're going to multiply it by a scalar, in this case 5. So we're going to do 5 times u. And get ready, everybody. This is rough. So our new vector, it's extended out. It's 5 times as big. So the x component's 5 times as big. The y component is 5 times as big. And the z component is also 5 times as big. So that's scalar multiplication by a vector. And we've gone into 3D here, so just be careful. Okay, so addition, subtraction, multiplication by a scalar, pretty easy. And then addition and subtraction by vectors that have been multiplied by a scalar is pretty easy as well. Okay, these are going away. Got extra room. I don't like all this competition on the board. There is a thing called a position vector, okay? So we can define our vectors based on start points and end points sitting out on the Cartesian plane, but we can also have a position vector. And when we say position vector, we're literally meaning on the Cartesian plane, the tail is at the origin. Okay, so it's got a very specific position on the Cartesian plane. So if we wanted to find the position vector equivalent to vector AB, if A is at 1, -4, and B is at 3 and -1, first of all, let's find out what the components of this vector AB are. Okay, so we're going to draw it, because oh man, we're maybe not going to draw it that well, but we're going to draw it. Okay, so there's AB. We just have to find out what the components of this vector are. And then we're going to draw it at the origin and turn it into a position vector. And so what is the, basically, what's the x component of this vector? So we're going from 1 over to 3. What's the x component? If you're saying 2 right now, good for you. Yes. Okay, so in the x direction, we've gone 2, and we've gone from -4 all the way up to -1. And so the y component of that vector is 3. And so if we want to draw this as that special thing called a position vector, we go over 2 and up 3, and we draw it with its tail at the origin. And here comes the same vector, but we're going to call it u this time. And it's 2, 3. Okay? So vectors, we don't actually necessarily, we say these two are equivalent. They should be parallel. They're not, but that's probably because of curvature of the Earth changing the way they look. Okay, We say this vector and this vector are equal. Even though they're in different places, they are equal. We call this one a position vector because its tail is at the origin. They are actually called equal because they have the same direction and the same magnitude, and that is the definition of a vector, okay? And tail at the origin is the definition of a position vector. Weird, right?
So if position had a definition vector, then it wouldn't be equal.
That's right, yeah. So if position came into it, those two would not be equal. Okay, all right. So those two are equal. Good. I'm going to do a quick overview of finding out if 3 points are collinear, and we're going to use a vector argument. So our 3 points, carefully selected from a variety of points. So P, which is -1, -3. Q, which is 0 and 2. And R. So this is actually the pirate point R. There we go. So the question is use vectors to determine if these points are collinear. R. Oh, I spelled R wrong. Look, I spelled it wrong. It should be R. No. Collinear just means they're all going to lie in a straight line. So I could draw a line that all 3 points would lie on. Okay? So it's going to look, it is going to look, if they are collinear, -1, -3, 0 and 2, and then if they're collinear, that third point should lie out here. Yeah, so what I'm going to do actually, if this is P and this is Q and this is R, I'm going to compare PQ. So I'm going to compare vector PQ to vector PR. Okay, and basically try and figure out if they're the same vector, but they're scaled out. Okay, so PQ. I'm going to convert this into a nice. I'm going to convert this into a nice position vector, and so we're going from -1 up to 0. So that's -1, and oh yeah, we're going from -3 up to 2, and so that's 5. Good. Hope I haven't made any mistakes. I can't hear Maddie to tell me if I've made any mistakes, so I'm on my own today. All right.
Mr. Rogers.
Uh-oh, did I make a mistake, Johnny?
Just, if you go from -1 to 0, is that -1 or +1?
So if I go, oh, look, if I go from -1 up to 0, oh, yeah, look at that. You're right.
Nice.
Look at you. Yeah, so PQ is 1, 5. Thank you, Johnny. Okay, so PR. That was really bad PR right there. All right, and so I'm going up to from -1 to 3. So that's 4. And I'm going from -3 to 17. And so that is 20. Okay. We now have just about enough information to determine if these are collinear or not. So they all share a tail. We just need to figure out, are they parallel? So if they're parallel and there's a point that is common to both vectors, then those points are going to be collinear. And so if I look at vector PR, I can see it's actually a scalar multiple of PQ. Okay? So basically, although the magnitude is greater, they have the same direction. And because they share a point, so there's a common point. Oh, common point P, and the vectors have the same direction. These are collinear. I think I'm spelling that right. Okay, let's go.
Can Manny ask a question or should he wait?
Pardon me?
Can Manny ask a question or should he wait?
If he can wait like 3 minutes, I think I'm going to be done.
Okay.
Yep.
Okay.
4.
All right. Last question. Last example problem. So this is a parallelogram problem, and we are going to work in 3 dimensions. And we are going to complete a parallelogram. All right. So we have a point A, very Canadian point A. And this is 1, -5, and 2. And we have a second point B. And point B is -3, 4, 4. And what we want to do is we want to use those points to make a parallelogram. So here we go. I'm going to draw the 3D axis. So make sure you've got your 3D goggles on. So by convention, Z's going up, Y is going that way, to the right, I guess. Here we go. Here comes my x-axis. Just be careful, everybody. Okay, there it is, coming out of the screen. Okay, so here's my point A over here. 1, -5, and 2. As you can see, I've carefully done the projection here, and here's B over here, -3. -3, 4, 4. Okay, so I have a vector there. I have a vector there. And in 3 dimensions, what I actually want to do is I want to find out where the last point of the parallelogram would be in order to make this, to complete this as a parallelogram. Okay, so where exactly is that point? Okay, so this is easy because I can just use my parallelogram law and I can draw this line right through my coordinates that I thoughtlessly put right there. I can actually add this vector and this vector together to find out where that point P is, okay? So I'm going to call this one U, and I'm going to call this one V. And so the last point is going to be where U plus V is, okay? All right, so U is 1 minus 3 is the x-coordinate, and -5 plus 4 is the y-coordinate, and 2 plus 4 is the z-coordinate, okay? So it's -2, -1, and 6 is the coordinate up here to complete my parallelogram. So -2, -1, and 6 is that last point. So I've just added U and V together to get to the last, to find out what that vector is there. And I've found the last point in the parallelogram. Okay,